Welcome everyone. Thank you for attending this webinar. Today I'm going to talk about modeling of root-soil interaction of tree biomechanics. My name is Jonathan Ramos Rivera. I'm a senior geotechnical engineer in EPM and also a lecturer in Universidad EAFIT from Colombia. Today I'm going to discuss or try to show to all of you a case study in Singapore when we try to analyze and model the root soil interaction in trees. And the main focus on this point is that we actually try to reproduce the real root structure. So in the next slides, I will cover all these things and all this content with you. Okay, this is a brief summary of the content of this webinar. First of all, I will introduce a brief introduction about tree stability and tree failure. The second, I will try to link the climate change and the tree failure, trying to relate it with the wind load and the loads that the tree experience in the field. The third point, we will see some approximation or some approaches about the numerical simulations. In this case, we will discuss a case study again for a pulled tree in Singapore. We have a lot of trees pulled there, but in this case, I will only show to all of you the one specific tree. And the last one, we will discuss the results and conclusion of this study. This is just a first, as I said, first approximation or first approach, but we are actually doing more tests and more analysis in order to increase the amount of information or the amount of data in this case. This is a brief summary about me. So I think a generic paragraph about me is I'm a civil engineer from Colombia. I have a degree in civil engineering and a Master of Science in Geotechnical from National University of Colombia. I also have a consultancy experience around 10 years of professional practice in the field of large infrastructure, mining, and hydropower projects with a focus in geotechnical dam engineering and mining projects. As you can see, this experience is also supported by a previous work in Singapore with Nanyang Technological University and also a department inside that is NURI. This is the Nanyang Environmental and Water Research Institute, in which one I develop a project related to climate change, unsaturated soil mechanics, and also tree stability. Okay, about the company information where I currently work. I work in Empresas Públicas de Medellín, whose brand is EPM. This is the largest multi-utility company in Colombia, with market-leading business in power and water sectors. I'm also a lecturer in Universidad EAFIT. EAFIT is one of the most prestigious private universities in Medellín, Colombia. It is approved and recognized by the National Education Ministry, and the university's main campus is located in El Poblado, Medellín. Okay, now let's go to the focus or the big point here. So I will try to introduce some basics and antecedents of why it's important the details and the study of tree stability. And in this case, I will try to show you that is not an uncommon thing, this tree failure. This is basically represented every day in our life. And I will try to show you some particular cases, one in Singapore and the other one here in Colombia. Before that, let's talk about the stress distribution loads on trees, forces acting on the root soil interface, and also the concept of tree population. In figure 1, you can see the stress distribution based on the deflection of the root soil plate in terms of degrees against the turning moment. The maximum static bending moment resistance of the tree is dictated by three components. In this case, we will see the soil strength that is characterized by the resistance and the soil tension, and the strain of the inward of the roots. The trunk strength but will be basically the weight of the root soil plate and also the soil shear, and a complex root soil interaction that is driven by the resistance of the hinge. So in the second case, or in the figure 2, you can also see that like trees sway under wind loads, under wind light conditions, the trunk of the tree hardly deforms. However, large motion of trees observed in the branches of the canopy. In some cases, severe wind conditions can trigger excessive bending moments that may result in local or whole tree failures. Whole tree failures can be in the form of breakage of the tree trunk if the roots are strong enough to resist uprooting, or uprooting if the reverse is true. In this case, we will discuss in this session the condition about how is this case not considered as a tree population, but is considered as individual trees. For example, in urban areas, there are occasions in which individual trees can fail under the influence of high wind loads and can cause inconvenience or pose a danger to people and property. A large part of this urban greenery comprises thousands of mature trees in Singapore that can be found growing along roadsides, parks, and within residential, industrial, shopping, and business districts. In this case, to ensure a sustainable and harmonious coexistence, detailed comprehension of tree biomechanics response under different environmental laws is needed. So that's why tree stability or tree failure analysis is required for a city. In this case, as I say, we will move forward to the next slide. So in this slide, we will discuss how is the antecedent of this event. So this is normal. This is a normal condition. This is a normal condition. We will have to take into account the conditions of the stability, or this is something that we cannot manage. Let me introduce this photo. This accident took a life of 38-year-old woman from India. This photograph is taken from the Botanical Garden in Singapore. This photograph is taken in 25 of July of 2017. In this case, we have the tree failure. This is a condition that doesn't want to expected inside the Botanical Garden. It was after a rainfall condition, an extreme rainfall condition, that we experience a tree breakage, and in this case, we have a casualty. So let's move to the next one. This is a photograph taken in Colombia. This is an uprooting condition due to the heavy rainfall. We have a close local neighborhood that was affected by this condition. We didn't have any casualty. However, we have some infrastructure and local damage in the place. Moving to the next one. So we will have another tree failure condition. It was on 23 of April of 2019. This condition was surprised. Also, we have a casualty. This tree suffered uprooting due to a heavy rainfall condition again. And this was located in Cucuta. This is a municipality of Colombia. And in this case, we have a casualty and also have a physical and infrastructure damage condition. Okay, so now let's try to make a link between the rainfall and temperature conditions, and what is the impact in the climate change, the tree failure stability. So as you can see, these videos taken from NASA, we can see in the left the projection of the temperature condition in a window from 1980 from 2018, and to the right we can see how is the rainfall condition, or what is the expected rainfall condition in the world during the next years in a projection or in a window from the 19th to 2040. As we can see in both cases, the rainfall condition will be concentrated in the tropical zones. Even in the final simulation, that is 2040, we can see like the extreme and severe conditions of rainfall will be in the tropical zones. So it will impact on the climate change of tree stability, basically in the loads that the tree will experience based on the storms, and also the wind load will change during these conditions. So right now, for example, in my country, Colombia, we are experiencing a huge amount of tree failure due to rainfall, but this is not a new concept or a new thing. We already have mapped this condition, but we have taken into account some remedial measurements to attack the problem. So in this condition, we can see that the rainfall and temperature condition will get worse. And also, that means that in the future, we will experience more wind loads. In that case, for example, for the next case study, we analyze some trees in Singapore, try to figure it out how will be the main conditions or the main particularities that we need to have into account during the root soil interaction. We have some previous works, for example, Gardiner, De Vosses, and other authors, basic on trees from the agricultural point of view. However, trying to manage or to transform this agricultural point of view to the geotechnical and also the structural point of view, we try to simulate the real root architecture. So this means that we didn't have any, we have access to the real root, basically failing some previous trees. And in this case, we analyze using 3D laser scanner just to analyze the routing architecture. But we can see this in the next slides. So what is the problem statement about tree stability? So basically, trees, as they age, naturally develop defects. Often, these are of little significance in terms of tree safety. However, some defects, particularly those associated with the main trunk and structural roots, have the potential to cause a whole tree to fail. In this case, if we have pedestrians, we have infrastructure, or we have people running around, we will have a higher risk of to create an impact in the society or in the country. So the main focus of the risk safety analysis will be to prevent these conditions. So although infrequent in the urban environment, it is the failure of a whole tree that has the potential to cause greatest damage to harm to people and property. So this is like the same conclusion I said before. The main point here is that we need to prevent it and also protect the people and the property. So I already extracted from several for some journal papers some conditions or some conclusions about tree stability that support my decision or support our decision to try to prevent the tree failures. So for example, Rojarjo in 2009 say that the increased incidence of trees uprooted during storms are the main reasons for the increasing research interest in this topic. In Singapore, the number of tree failures every year is more than 1,000, and those due to an uprooted condition are close to 20%. So if you can see that in Singapore, the main conditions, every year we have 1,000 trees failing. Basically, it's not the uprooted condition, but we also have a different kind of tree failure mechanisms, but the 20% is a higher condition that is associated or related to heavy rainfall. So we have Yang in the 2014. He said that the windstorms are the major natural hazards affecting European forests, causing tree damage and timber losses. Modeling tree anchorage mechanisms has progressed with advance in plant architectural modeling, but it's still limited in terms of routing distribution, strength, and numerical models. So it supports the necessity of the, as Prof. Rahar just said, that there is an increasing research interest in this topic, and the root soil interaction due to rainfall is extremely important to try to identify which conditions will trigger a tree failure. So finally, Gambiastini in 2018 added that in addition to the increasing temperatures and exacerbating meteorological extreme events, climate change affects the frequency of windstorms, which impact the stability of trees. Therefore, there is growing interest in developing models for predicting how to anchorage could influence tree stability. So these three extracts from different research papers will summarize in the same thing. We need to increase our knowledge. We need to gain new knowledge in order to analyze how is the tree behavior, how it will behave in terms of strength, and how will be the approaches that we need to have in order to recreate the real conditions in the field. So finally, the understanding of how trees respond to the lateral loadings, in this case wind loadings, is required for the effective management and selection of risk mitigation strategies for mature trees and even young trees. So in this case, or in this webinar, we will see a brief summary of a study when we analyze three tree species commonly found in Singapore. Which one we are going to, I'm going to show to all of you is the Samania saman. We started using static loading tests, air spading, and laser scanning for the resulting geometries. And we try to combine all this data that we gathered, and we analyze it via a finite element method using MIDAS GTS&S. And we also have strength properties, soil properties, in order to currently understand the behavior in place. So now let's move to the main thing. So the numerical model simulation. So in this case, I will try to show all of you the model setup, the meshing condition, and I will also give a brief summary of our conditions. Before that, I will explain how was the static loading test and bending test conducted in the place. So the static loading tests were performed using a rope attached to the tree at different locations. So as we can see, this is the main picture of the tree pulling test. These locations were along the trunk to apply controlled static lateral loads to the tree. We based this test from similar authors like Peltola, Kochi, Gardiner, and Stokes. These lateral lobes were measured using a load cell in line with the pulling rope and an LVDT attached to the tree. So the applied lateral loads, deformations, and geometry of the tree were recorded and used to compute the strain parameters, strains, and stresses developed with the trunk to estimate the overall stiffness of the tree and anchor it to the ground. A series of also 3-point bending tests was also carried out in the branches and in the tree in order to characterize the modulus of rupture. So moving to the soil type, the soil of the experimental site was characterized by its particle size distribution. This distribution was performed of 3 samples. And the soil foundation was composed of medium sand with a medium particle size, D50 around 0.4 mm, and a coefficient of uniformity around 3. The grain's shape was characterized as rounded particles with medium sphericity, and the fine content were less than 10%. So for the stress strain condition, we measured the stress strain response curve obtained from the triaxial test conducted on a saturated soil specimen. We also measured the hydraulic conductivity and the SWCC curves, so soil water characteristic curves, in order to analyze the rainfall condition. So let's talk about the model setup. So for each tree species that were air spread, the actual root architecture was very different in terms of type, depth, and orientation. The root architecture, in this case, as you can see in the picture, was captured through laser scanning using a B-line 3D terrestrial laser scanner, or TLS. It is capable of providing data with an accuracy of 5 mm. This configuration is collected in a point cloud, and this point cloud was post-processed in order to obtain the final configuration of the routing architecture. So it is important to mention that because of the difficulty of the reconstruction of the root architecture, the roots of the third order and higher were removed from the analysis. So it means that we will only see the main root structures, and we will remove all the fine roots. It obviously will imply some variation of the real behavior of the trees. However, this is the best thing that we can do in the MIDAS GTS analysis in order to get reasonable results. So after having the point cloud condition, so we use pre-processing and post-processing and also reconstruction and meshing of the point cloud. In this case, we use Mesh Lab and Cloud Compare in order to create the mesh and also creating the solid. In this case, we have a solid with not high accuracy and also some errors inside based on the numerical and the photographs of the tree. So we managed to refine the tree mesh and also the tree solid in this software in order to have the closer or the near real structure of the tree. So this is finally the pictures of the reconstructed real root architecture once in MIDAS GTSNS. So we managed to import as a IGS file from a CAD version, and we easily imported in MIDAS GTSNS. So one of the main things, the bottom pictures. This is the Samania Saman. So this is the tree. I'm going to show you the results for the analysis. In this case, this rooting system of Samania Saman had more structural roots that provided by the stability of the tree. In this case, the average diameter of the roots were about 0.2 meters or 20 cm for the first ordered root. We have 4, 1, 2, 3, and also 4 structural massive roots in a radial conditions. The depth of the rooting system identified during the test was about 1.2 meters, and the thicker main member of the root structure has numerous secondary lateral roots. However, as we decided, we'll try to remove of the third order and higher in order to have reasonable results in MIDAS. This is not a limitation of MIDAS. The thing is that if we have more fine roots, we will once we will try to reconstruct the mesh and also reconstruct the main roots. The software, the Cloud Compare and Mesh Lab, recognize that the fine roots are a structural member. So in some cases, it identifies thicker members that was not real. So we decided to remove the third order and secondary order fine roots. So in this case, we are only seeing structural roots. The concept of structural roots means that these roots are providing the stability of the tree. So we will move to the results section, but previously I think it's important to know that the values and the directions of the applied displacement in the numerical model correspond to those applied in the field test. Also, I think it's important to mention that we in the model the sand was considered to have a homogeneous elastoplastic material in accordance with the Moore-Coulomb strain criteria. And I think it's important also to know that we consider for the rainfall and matric suction condition. So in terms of matric of suction interface, we use Bishop stress. As mentioned in another webinar that is well explained. We use Bishop stress, and also we managed to incorporate the change of a young modulus due to matric suction. This is an approach that is presented by Rojarjo. But in this condition, we try to manage how will be the change of the elastic modulus basically on the matric suction condition during a rainfall event. So we will see some results in this case. So just as to summarize, we have this Kaya senegalensis tree. The trunk diameter is around 80 cm. We have an average root diameter between 0.1 and 0.15 meters, and we have an average trunk diameter of 1.4 meters. For the Samania Saman, this is the case analysis. We have a trunk diameter about 0.6 meters, and we have a rooting depth. This is the rooting depth of 1.2 meters. I will rephrase this. This dr is the rooting depth, so it's 1.4 meters. So this means that it's 1 meters below the ground. And also in this case we have an average of 0.2 meters in terms of the thickness of the rooting system. So in this case, just to summarize, we have a number of nodes, or this is the number of nodes, number of elements. We have two running conditions. The first one is using a conventional laptop, so it means that it has 16 gigabytes of RAM, and we use an Intel Core i7 to run these simulations. In this case, for each tree, we spend around 3 hours running each case. But later on, we manage to create a AWS server. This is a server created by Amazon, so we practically can use any kind of specifications of our laptop. It obviously have more cost, but we reduce the running period from 3 hours to 30 minutes for each scenario. So in the model setup, in the left we can see the Samania Saman. To the right we can see the Kaya senegalensis tree. In this case, this is the boundary conditions. So we manage 3 meters below. We have 3 meters of wide of the analysis, and we also have our tree that is around 20 meters of height. In these conditions, we also manage to simulate 4 meters. So 4 meters is the extension of the routing system. In this case, this is the same 4 meters. I don't know why it's not in this picture, but we also manage and try to standardize the simulation. So we have Samania Saman condition, and we have the Kaya senegalensis tree. So now moving to the next slide, we have a big picture of how is the interaction and the boundary conditions. So in this case, we use bounded condition. We decided bounded condition in order just to analyze how is the linear equivalent condition of the tree routing system and how is the interaction with the soil. In this case, so we have the mesh. We have different kind of meshes and size of the mesh. For the tree, we manage every centimeter, and for the soil, we manage to every 10 centimeters in order to have a consistent results. So again, this is a big pictures of how it can be seen in MIDAS GTSNS. I think the picture is quite impressive. The results also are quite impressive, but we will discuss it later. So now let's move to the results and conclusion. So first of all, as you can see, you are seeing the stresses under a bone misses condition of the tree under the lateral load. This is this arrow is the direction of the applied load for the Samania Saman tree. So the model for the Samania Saman predicted that the dominant contribution of the main roots of the anchorage strength, whereas the secondary roots only develop around 10% of the maximum stresses presented in the main tree. So for Samania Saman, the root soil interaction behavior also highlighted that the increase in soil stiffness based on soil Young modulus can cause the stress of the base of the trunk increase, especially in the tension side. So we managed to analyze 4 conditions, considering the matric suction and the influence on the elastic modulus of the soil. So in this case, every analysis, so A analysis will be considering a first stage or the lower E modulus considering matric suction, and the D condition will be the higher E modulus. So we can see that every time we increase the elastic modulus of the soil due to matric suction and rainfall, the condition of the tree, as you can see here, will manage. We will see that there is a concentration of the tree of the stress of the tree. So it means that in any particular case, so in this case, as I pointed out before, the stresses are higher if the stiffness of the tree is higher. So it means that if we are experiencing higher matric suction conditions, so the effect of the structural roots will be higher. So in terms of wind resistance and tree stability and tree failure. So it means that when we experience higher matric suction conditions, we will have higher stresses on the roots. So in case of an extreme rainfall or extreme storm, we will experience some failure due to an uprooting condition, and we also have breakage at the base of the tree. So it was a great conclusion of the numerical analysis. One advantage of the numerical model used in MIDAS GTSNS was that it allowed the evaluation of the mechanical resistance and bonding transfer between the soil and the rooting system. So using numerical modeling, it was possible to estimate the effective length of the roots that provided structural resistance under lateral loading. So in this case, the threshold value used to define the tree protection zone that is called in agriculture was the minimum concentration of the stress, and limiting this minimum stress condition of the roots to the 5% of the maximum computed value. In this case, so the results indicate that only the parts of the entire length of the roots that offer resistance. So the magnitude of the resistance of the effective root lengths were strongly affected and strongly influenced by the soil elastic modulus. So it means that it will be strongly related to the matric suction or the unsaturated condition. So as I pointed out before again, so these contours, I think this is a brief approach or a rough approach. So these contours can manage to understand what will be the zone of the main structural roots that will be affected by the matric suction and also by the loading experienced during the wind loads. So in the next case, we will see again the same. So we can manage even increasing the elastic modulus. We will manage to select which places we can manage to protect the tree or the tree root protection zone, in order to have stability to the tree. So in order to finish this presentation, so the conclusions. So the numerical modeling showed that the contribution of the structural roots to the tree anchorage was primarily dependent on the first order root morphology. So it means that the first order roots or structural roots are the ones that guarantees the tree anchorage. So also the orientation of the rooting structure influence the results. The modulus of the tree and also the soil. We find that the numerical model was agreed with the tests that we did in place. So in this order, we understand that the influence of the lack of the soil strength in tension, the windward root zone undergoing tension was often larger than the leeward zone. So in the leeward zone, we will experience compression, and in the windward zone, we will experience tension. The other thing is that the tree root studies carried out using MIDAS GTSNS, we managed to link these MIDAS GTSNS with the real routing architecture using the laser scanner. So we try to simplify this routing architecture, and we have good agreements with the simulated tree and simulated routing architecture with the results with the MIDAS GTNS. So we also found that the direction of the routing zone in natural trees is also larger in tension, as I said before, and also the soil modulus playing a significant part when the routing architecture is weaker in terms of lateral routing diameters, and also number of lateral roots in line with the lateral load direction. So moving with the advantages, I think for the MIDAS GTSNS, additionally for the previous discussed, I think the geometry and modeling and mesh generation is very easy and fast. The analysis time was extremely short. As you can see, even running with a conventional computer. We managed 3 hours for running this analysis. This analysis has a high number of elements and a high number of nodes, but the time was short. Also, we can move to a AWS server or any online server that we can install, and we can decide which expect that we need for our computer. So it will be mean online and easy and eventually really fast. And also the output can be extracted very convenient and quickly. As you can see, my features were extracted from directly from MIDAS GTSNS. And also we can use tables and graphs in order to to sketch or just to think our main conclusions in order to draw in a paper or draw in our reports. And I think the last one, but not the less important, I think the 3D PDF function is really amazing. Not only in these terms of doing our research conditions, but in terms of interacting with our clients or in our team members, we can use everywhere this 3D PDF function. We can create cross sections inside the 3D PDF, and we can also give to the clients this file, and he can also manage and use it even without a MIDAS GTSNS license. So I think this is one of the main conditions, the main aspects of the MIDAS GTSNS, and I think it's not only MIDAS GTSNS, I think it's how it can be linked to our projects. In this case, we have a successful case study. This is not only a case study, it also began a new projects based on these conditions in Singapore that we are currently analyzing and doing using this software. So I think that's all. Thanks a lot for all the attendance, and I will be open to discussions or questions for the attendance. Have a good day.